2 microphones. You can hear me in stereo. Well, thank you, Bob Dickinson, for your very generous introduction. It means a lot to me, especially coming from Bob, who is really one of the heroes of his generation in atmospheric sciences. He really is. So I'll actually introduce you. Bob is the only scientist I know in the atmospheric sciences who's both a member of the National Academy of Sciences and the National Academy of Engineering. I don't know of any others. Vern Sumi, I believe, the late Vern Sumi had both. In any case, I'm really honored to have known him all these years and to cross paths and helped each other many times. So, now, thank you all for coming this week. After being delayed by a week, I'm in a book club, and I told them that I was going to miss last week on Friday evening, but then it turned out I had to send out an email saying that it was delayed a week because of a fear of a snow job over in... Now, that's such an old expression that I think probably only the old-timers in here know what that means. But anyway, you can ask if you didn't catch. Let's get on with this. I guess I'll use the clicker here. And so let's talk about these 4 things this evening. And by the way, of course, you know that climate is really in the news these days. It's all over the newspapers and the blogs and everything right now. Probably stimulated most by the Copenhagen conference that's going on right now in Denmark. But of course, there have been many things that have sort of sprung up over the last few weeks. And while this talk was prepared and shipped over here a few weeks ago before any of that flap occurred, I am more than willing to answer any of your questions about the hacked emails or whatever you'd like to bring up. But let's save that to the end and get on with the talk as I had originally planned it. So here are some things that I want to go over this evening. One is that I think that the climate change that we are experiencing is really real. It's happening. I think there's really very little doubt about that, even among most skeptics. The Earth has been warming over the last century and a few decades more. And number 2, I think this is going to continue into the future, so I'll give you some ideas about that and why we think that's true. And that, in fact, there will be an impact here in Texas. Of course, as I get down to the scale of Texas, our predictions are a little less certain, and there are a lot of other things that are uncertain about climate change. So I want to try and be honest about that part of it tonight. And so finally, the last thing that I'll touch on at the end, especially for the younger people in the audience, is what are our choices here? What should we do? And of course, that comes back again to Copenhagen. So let's be on with it. Actually, Jay, thanks for setting this up and helping me to get this presentation together. One thing they wanted to make sure is that everybody understands what climatologists mean by anomalies. When we see fluctuations of the climate system, they're always going up and down. Usually what we do is we compare that with some long-term average, say a few decades or sometimes a whole century and so on. So the anomaly, when we refer to an anomaly, we're talking about the deviation from some kind of long-term average. All right, so here is the temperature as estimated over the last century and a little more. And what you see here are the red bars are the estimates coming. This comes from the National Climate Data Center in Asheville, North Carolina. And the red bars are the best estimates of what the temperature of the global average was, annual average and global average was. And these little I-beam looking things here are the errors that the assemblers of this work think that are reasonable. Those are probably plus minus 1 standard deviation, or maybe a third of the. So getting outside of that is possible. It could be that their error is as large as those and maybe even larger. And if you have a look, you'll see that the error bars, these things here that I'm referring to, they do get a bit narrower. A lot of the estimation error comes from lack of coverage, and there are also some biases that have to be removed and so forth. And of course, that's part of some of the criticism that's coming just in the last couple of weeks. So if you look here, generally speaking, what we're talking about when we talk about global warming is this kind of trend here. So not the ups and downs so much, but the longer term trend. Our climate models, and we'll see this in a few minutes, our climate models really are not so good at doing this part, and we don't expect them to. So sometimes they can do part of it, but not all. So this is going to continue. I'm just going to show you a few introductory slides before we get into the nitty-gritty. But here is a slide that comes from the Intergovernmental Panel on Climate Change, the IPCC, the notorious IPCC. And I'll talk more about that process and how it works a little bit later. But these here are the data going from the beginning of the last century up until the turn of this century. So these are actual data, and of course the gray here is an estimate of uncertainty, and then as we go forward into the future. So, and I think this probably are model runs, and the swath indicates the spread among different climate models in reproducing this time series of measured temperatures, the black line. And so if you look at this particular simulation forecast out into the future, this is the one that's called business as usual. So this is what would happen according to our models. On the right-hand side is temperature change, and so this is an anomaly. You see a difference from this average, not the actual temperature, but the deviation from, and from the present temperature right here. And so over here is Fahrenheit degrees, and over here Celsius degrees. But this is business as usual. This is what the models would say might happen if we continue putting carbon dioxide into the atmosphere and other greenhouse gases at about the same rate that we're doing now. You can't, of course, predict climate into the future without knowing what people are going to do. So you have to know that before you can actually do that. So we have to go to economists or others to tell us several different scenarios of what might be the human behavior during this period. So the second one is a more moderate one in terms of putting CO2 and other greenhouse gases and aerosols, all of the human aspects of it. And then a low CO2. This one is an interesting one. This is one where the models hold the carbon dioxide constant over the next century. And what you find is, and the other greenhouse gases, and what you find is that it actually continues to warm a couple of tenths of a degree, and this continues out over the next couple of centuries. And so people refer to this warming that will go on even after we hold the carbon dioxide constant as the commitment. So we actually have already committed that much warming into the future. So what is it, and then my third point in the introductory slide was that this is going to impact Texas. And now, as I also warned you, we don't know as much about this because we're now getting to slightly smaller scales. But I think there's enough evidence to suggest that at least qualitatively we've got some handle on this. And notice that in Texas, all the rivers run across this way toward the Gulf or toward some other river that takes them to the Gulf, takes water to the Gulf. So it is very important that there be water out in this part of the state that feeds these rivers coming across. And one of the things that we're going to see is that out in West Texas, it's likely to end up being drier than it is now. And it could very well be, it's my own contention, but it's really a conjecture more than anything, is that in the eastern part of the state, it may be wetter. Well, these two may be an exaggeration. I don't know if it's going to be quite like that. But there is evidence that there will be longer periods of extremes toward the end of the century than we've seen in the past. That does seem to be a fairly robust feature looking across the 20 or so big climate models that we use. And so what about our choices? What should we do? What's going to happen? Well, I suppose we could buy a lot of this stuff and kick back and take it easy on the front porch with a margarita, or we could take responsibility and try to do something about it. That may be wise. I think it is. It may be cheaper, in fact, to do that in the long run. And in fact, there might even be a number of other advantages to doing something now. So we'll come to that toward the end. This is a graph that was produced 3 years ago by a committee of the National Research Council, and Bob and I served together on this committee. And this is a depiction of what this committee thought the temperatures have looked like going back over the last 1,000 years. And I really like this graphic, so I'm going to talk about it for just a minute. What we're seeing, what you see here is the temperature anomaly. So this is the deviation from the long-term average here. And what you see is the present climate temperature, the global average. This is actually the average over the northern hemisphere, and a pretty rough estimate, we all know. The black line here is our instrument curve. So this is that last 100 years, essentially, that you saw on one of those first graphs that I showed, the black line. Then there are a number of other indicators that we have that we call proxies that we can kind of tune up to the instrument record and use them to go back into, in other words, find out something about the thickness of tree rings, for example. And what we find is that certain trees, when in certain climates, such as at the top of a mountain or in high northern latitudes, they're stressed by the temperature. So in other words, they're right in a zone where if it's a little bit warmer, the tree has a very good year. If it's not so warm, the tree doesn't have such a good year. So if you look back at the width of tree rings, at least in some places, it's a good thermometer. And so what people have done in the late 90s and early part of this decade is they have trained their tree rings using the instrument data where they overlap, and then they were able to go back in time to make estimates back here. But there are a number of indicators here. This one, for example, is from boreholes. Actually, that's the blue curve. You can actually find holes where people for mining or petroleum engineering have put deep holes in the ground, and there are logs from these wells of temperature going down into the ground. And it's a fairly straightforward physics problem that if the surface is being warmed, temperature going up, that diffusing down into the ground can be, if you have that temperature record, you can invert it and learn what the temperature was back in the past. Well, it filters out the big ups and downs, but on the other hand, you do get a rough curve like this. And there are literally thousands of these holes around the world. It's very noisy, but when you average them all together, away goes the noise, and out comes this really rather remarkable signal. And it seems to work for each individual continent separately, so that's a rather nice, completely independent measure. Another one is glacier lengths. This is a Dutchman, Earlman's, and his is the dark blue curve. What he found was that looking at hundreds of glaciers around the world, that the length of the glacier, mountain glaciers now, the length of the glacier is strongly correlated with the temperature. So here's yet another independent measure. Another one is ice cores taken from Greenland or Antarctica. It's possible to use oxygen isotope as a measure of the temperature when the snow fell to form the ice sheet, and you can actually count your way back in time because it's easy to see the annual layers just as you can with tree rings. You can count your way back in time by going down deeper into the ice core. So there are people who've done studies of those in the tropical glaciers as well as the polar ones, and so that's yet another. So these, as we go further back in time, though, the tree rings seem to be the most reliable. Maybe actually the ice cores are the most reliable, but the ice cores don't cover very much area, so can't exactly make a global or a hemispheric average. On the other hand, the tree rings are problematic. We don't know exactly the physics, the chemistry, the biology going on. And so one thing that has received a lot of interest in the last few weeks is when you look at the tree rings, they turn over about here. So we'll talk about that later in the questions if you want to bring that up. But this was talked about at great length in the committee. Bob will remember some of those knockdown, drag-out discussions that we had. So climate is constantly changing, and fluctuations are a natural part. And so I want to come back to that same graph that we looked at before and actually put the trend line on. Notice this one has a slightly different slope because every time I draw it, it has a slightly different slope. But I think that's a measure of how much we know about this. That's fine. And if you look at the little yellow blotches here, these are really what we would call in the business the natural variability. And for example, 1998 is the warmest year on record. Well, why was that? Well, it turns out there was a big El Nino that year, and when there's an El Nino, it is so strong out in the Pacific and other places that it influences the entire global average. So natural phenomena that we are really pretty well aware of happen every few years, and they do drive an extreme this way or that. Another thing that causes dips, and if you look, you'll find Mount Pinatubo right here somewhere. One big dip was Mount Pinatubo in 1992, and so when we have a big volcano, it can make a huge influence for several years, and then finally the climate recovers and gets back on this track. And you might also have heard, and it's true, that the temperatures have kind of leveled off in just the last decade. Even though this decade has been the warmest on this record, still it has leveled off a bit, and I would expect that that might continue a while before it gets back onto this track. So it's not a contradiction. It doesn't say the climate models are wrong. There's no way in the world that they could predict when an El Nino is going to occur, or many other chaotic elements in this very complicated nonlinear system. But it does appear that for these tiny changes in the radiation balance at the top of the atmosphere, that it's just almost a linear kind of response to the forcing, what we call the forcing. So in other words, the imbalance of the radiation. So now let's turn to that issue. This is a cartoon that shows you, and I'm going to give you one in a little more detail on the next slide, which I hope doesn't drive you out the doors. I promise it'll be the only one that's a little more than you might want. But some of you will like it, I hope. Maybe Bob, I took the wrong foo. All right, so this one shows us the balance of incoming and outgoing radiation. So basically the sunlight comes in, and about 70% of it is absorbed by the Earth atmosphere system, and about 30% is reflected directly back and has no influence at all on the climate of the Earth. But of course we can vary the reflectivity of the Earth, the so-called albedo, and that will change slightly the amount of radiation absorbed by the system versus that reflected back out to space. Then this rate of incoming absorbed radiation over a long term has to be balanced by the rate of radiation back out to space. Well, the Earth happens to be a warm body, just like the sun is a hot body, and radiation does emanate from the Earth's surface, but it's intercepted by these greenhouse gases and clouds and might be reflected or even absorbed by some of the particles in the atmosphere. So when that happens, this radiation in the atmosphere is radiated back down as from the bottom of clouds, but also out to space. And the net effect of this is that it reduces the amount of radiation out to space compared to what it would be if the Earth had no atmosphere at all. And I'm going to illustrate that now on this next slide, which has a couple of... this is from an ancient paper that I wrote. It's almost paleoclimatology of climatology. It's so old. This is back in the 1990s with Graves was a postdoc of mine at that time. And what this one shows is the outgoing radiation in watts per square meter. So this is a number that you can hang on. One of these lights here, especially that one shining in my face, might be about a couple hundred watts per square meter. And down here is the surface temperature. And if the Earth had no atmosphere at all, this curve would be the famous T to the fourth Kirchhoff law, Stefan Boltzmann law, T to the fourth, where T is the Kelvin temperature. So you would get a curve something like this. In this range, it's almost linear. But if you look down with satellites, which we had already plenty of in the early 90s, this is a kind of density plot. And this is a very crude model. Please don't take this to be the whole story. It's really only a kind of gimmick that helps us to see qualitatively what's going on. So this is the radiation out to space versus the surface temperature. So these data were collected by satellites, and so there might be a point on the Earth where the temperature was right at freezing, and so that would be the amount of radiation going out from that point on the Earth. And you might look at different seasons and different latitudes and then reconstruct this plot. So roughly speaking, we would have a relationship between the surface temperature and the total outgoing radiation, something like that. Now, if we wanted to know where the Earth's temperature is going to find equilibrium, what we would do is find the bar across here that's essentially independent of temperature, for our purposes anyway, and say, well, the amount of solar energy absorbed by the Earth is about 235 watts per square meter. And I realize I'm making a kind of approximation here to say the Earth with no atmosphere would have exactly the same reflectivity as if there were an atmosphere. Actually, it probably would not reflect back quite as much because of clouds, but that would at most move the root up here a little bit. But my point is this: where these two rates of solar absorbed and the radiation out to space, that would give us a planet with a temperature about minus 20 Celsius. In other words, an uninhabitable planet. So, I mean, it would be snowed over, except that there's no atmosphere to snow on it. So, and if the Earth, if those clouds were not there and so on, well, maybe this would be up here a little bit, so it might be a little warmer than that with no clouds at all, but it's qualitatively the same. Now let's go over here. In the real Earth, assuming my toy model here is correct, and this is not the one that Bob referred, this is really a toy model, but it just is here for illustrative purposes. You see, the root here with our atmosphere, with its clouds and so on, is way up here, a temperature closer to some 15, it's actually about 14 degrees in reality, but not bad for a model as dumb as this, right? You get about the correct temperature of the Earth by just equating the rate absorbed with the rate being radiated out to space. So this warming from here to here is what we call the atmosphere effect. That's what I call that anyway. Now what happens though if we raise the carbon dioxide concentration in the atmosphere? Again, very crudely speaking, what happens is this regression line, if you could call it that, moves parallel down a little bit like this. So what the upshot of that is the root that was here moves over here. So in other words, when we talk about the greenhouse effect, we really are talking about a little nudge. We already have about this much, or maybe from about minus 10 up to here, and we're talking about increasing the temperature a couple of degrees. So that's the story. That's really what we're talking about when we talk about the greenhouse. So here's the boost we get from having an atmosphere at all, and if you increase the carbon dioxide a little bit, you're going to nudge it up a tiny bit more. So see, this is not some giant miracle thing that we're making a revolution, a catastrophic change in the atmosphere. It's a little nudge of something that's already been happening, and we couldn't have lived without it here. We appreciate it. All right, so what are these gases that are doing the job for us? Well, first of all, this is showing us again, I hoped in watts per square meter, but, well, down here, watts per square meter. And this is a little bar graph that tells us how many watts per square meter have been contributed by carbon dioxide in our atmosphere since the beginning of the Industrial Revolution. So you can see here it's about 1.6, I think, watts per square meter. And if you think about it, I don't know how much this is, but probably about a watt per square meter, something like that. I'm not sure. A Christmas tree bulb, that's about how much the CO2 has done for us. And the other greenhouse gases like methane, nitrous oxide, and now a lot of halocarbons are going into the atmosphere. While we've changed our refrigerants from the bad guys that destroyed the ozone layer, which Bob used to do a lot of work on early in his career, I believe. He started up there, and we finally have him back down to the surface. In any case, so altogether, it's a few watts per square meter, the greenhouse effect over this last century or so, last century and a half, since the Industrial Revolution. So water vapor. Now what happens? When you put in these greenhouse gases, you warm the planet a little bit, maybe 1 degree for doubling carbon dioxide. It's about 1 degree Celsius. And in fact, most of the skeptics, including Professor Lindzen, that's his estimate along with mine and many others. So when you put in this stuff, the temperature might go up the order of a degree or something like that. But what happens when you warm the planet a bit? Well, the relative humidity, our experience tells us that relative humidity tends to stay the same when you warm the atmosphere a little, the relative humidity. But you know, when you warm it a degree, the amount of water vapor that can occupy that volume goes up exponentially. So this is a big effect. You warm the place just a little bit, the water vapor goes up a lot. And so the water vapor here actually acts like a feedback, a positive feedback in the system. So this is what most climate theorists believe, is that water vapor is a positive feedback in the system, and that it also, by the way, is a greenhouse gas. See? So when you warm it a little bit with these anthropogenic greenhouse gases, you warm it a tad, you now increase the amount of water vapor, so you warm it even more. So that's the reason for the larger warming than 1 degree when you're going into the future. So this is a major component in the system. There are some other feedbacks as well, but this is probably the biggest one, water vapor. All right. So here is a picture of what we think has happened to carbon dioxide. This comes from ice cores in Greenland and Antarctica. And what happens with the ice cores is that the tiny bubbles that are trapped in the ice can be analyzed on today's accelerator mass spectrometers, and we can actually find the concentration of carbon dioxide in these ancient climates. We can count your way back in time by counting the rings, or there are other ways of doing it too. Once you've got your carbon-14 and other things well calibrated, you can go back that way as a sanity check. In any case, over this period, the last 10,000 years, which is called the Holocene, from this point, this is about when all the glaciers in the northern hemisphere had been removed from North America and Western Europe, and things have pretty well leveled out during the Holocene, especially the last few thousand years. There might have been a man-made component to this. We're not so sure, but there's a very interesting theory around that, in fact, this was about the time that humans started clearing forests and things like that. But in any case, look what happens here. All of a sudden, we have this exponential increase in carbon dioxide. The red here is the instrumental record from the 1950s, the so-called Keeling curve. So it's been exponential in the last 100, 200 years, a little more. So this is a remarkable fact, and one of the most interesting things in the history of climate is to see how this forcing agent has increased. Well, the Intergovernmental Panel on Climate Change, which you're hearing lots about these days, I could take a minute or two to talk about that, but I don't want to go too long with it. This is this organization under the United Nations that involves 120 countries, and there are 3 working groups that work, and they come out with a report about every 5 or 6 years, and different countries nominate scientists to participate in it. Finally, it's winnowed down to a manageable number of people to write book chapters in each of the 3 volumes. I'm interested here mainly just in the science of one of the 3 volumes. And so these chapter editors and authors work together to assess, and these are working scientists who are actively involved in this kind of research. So it's not like the National Research Council report where you take 12 people and who are not involved in any of the papers or any of the research and try to produce as outsiders some kind of assessment. This is different. This is a huge report involving all these countries, and what you go to, the people you go to are the people who are working in the field. So it's got its flaws, but this is probably the best assessment of any kind of scientific state of the art in the history of science. I doubt very much if there's been anything comparable to it. And so they've been making these reports every year for every 5 years. So this is their synthesis report. All you have to do is put IPCC in Google, and you'll go right to it, and you can download every one of these. So this is the chairman of the last one, Dr. Pachauri, who's in the news again right now. And so I say, really, one way to find out, the only way really to find out, is to go and ask people who know the most about it. And so if you want to answer the question, is it anthropogenic warming or just global warming, you wouldn't want to go to ask the polar bear people, much as we respect them and are interested in what they have to say. No, the answer as to whether it is or isn't anthropogenic warming is back to this physics problem that I was showing you a few minutes ago. That's where the answer is. Getting the feedback straight, understanding what they are, understanding the different drivers, such as greenhouse gases or aerosols. They tend to cancel one another, and that's a big problem for us. So that's where you have to go to find out about this. And in fact, the Wall Street Journal, I read this in the Wall Street Journal, but I'm not sure they conducted the poll. They did ask some 3,200 scientists, I believe, whether they felt that there was the anthropogenic component in this or not. And I believe the answer was 82%. But when they narrowed it down to only people who work in this field, who publish in our leading journals, they had 75 people in their survey. Actually, there are thousands of us. But they had 75 people, and I think only 2 were in disagreement. So it was 97% of the people who work in the field, people who would know something about the radiation problem and the Earth balance problem. So this was the robust findings of the IPCC, and I don't want to waste time reading all this to you, but basically it's this: considerable confidence in these atmosphere-ocean general circulation models, providing credible quantitative estimates of future climate. Confidence is higher for some climate variables. Okay, so here, this is a 4 graphs of different layers in the atmosphere. And so I'll hit one more here to give you a little more schematic idea. The stratosphere is actually cooling. And that's very consistent with our thinking about climate. The very kind of budgeting that we just showed in that one graphic earlier, you can use to show the stratosphere should be cooling. And if you come down in the atmosphere, you see, notice there are some real bumps here. These are volcanic explosions. This is Mount Agung. It causes a heating in the stratosphere, but a cooling at the surface because it's blocking out sunlight coming in to the atmosphere, so it cools down here. But up here, there's a little bit of absorption by the dust particles or those aerosols put up by the volcanoes, and so it causes a heating up there. And so, and these are El Nino events in the lower troposphere, much bigger than at the surface, and not at all felt way up there. So this is a consistent picture. This is what we expect the atmosphere to look like, and it does. Here I want to show you some simulations. This is a kind of experiment where about 20 climate models were used, and each one of those yellow lines is one run of one of the climate models. The black line in here is the data, the global average data from 1900 to 2000, and up here is the deviation of the temperature. And the red line in here is the average taken over all of those models. Now the models had in them the volcanoes. Here's Santa Maria, Agung, El Chichon, and Mount Pinatubo. And so the models have that, so they all take their dips when the volcanoes occur. They can't really time the El Nino, so that a model cannot predict when an El Nino would occur. It only will predict roughly the statistics about how often they will. It's like doing a weather forecast. After 10 days, you can't forecast the timing of it anymore. 10 days. Let's make it 3. Okay. All right, so this one, though, has all of the anthropogenic, quote, forcings in it, and this one over here has none of the anthropogenic forcings. So had the Earth been cooking along with none of those, it would have looked like this, according to the models, and but this is where the data went. So this is a very, very interesting thing to think about. So now it's going to keep on going. That's what our models tell us. And here we want to know what's going to happen. Well, the past and present, they give us some clues to look into the future. Okay. But you really, in order to do it, you actually have to have these physics-based models. Basically, they're outgrowths of weather forecasting models, and I'll show you a simulation in just a minute. But the main point here is you can't do it that way. Crystal ball does not work. Okay. So climate models do help us to forecast several important variables. The future global and regional temperatures, they're getting now to the point where when we look at one model versus another across the 20, there are some features that are robust across those models, even at regional level, and I'm going to touch on some of those. Got to hurry, though. It can also help us with future sea levels. Most of sea level change comes from warming the ocean. It's about 4 kilometers deep, and if you warm it by a degree or 2, it will expand about 1 meter, very tiny. But this is something well known. You can go look in the chemical rubber handbook and find the expansion coefficient and actually do that for my class. It comes out about 1 meter. It's about what we're talking about here. Future global ice patterns, of course, could be predicted in principle. Future moisture distributions, getting tougher as I go down this list, but we do think that we have some ways of estimating this that have some reliability. So future changes in natural variability, well, won't be able to time those El Niños or hurricanes or things like that, but we may be able to say, well, maybe the hurricanes will be more intense or maybe they will be more frequent. But right now it's too early for both El Niños, in my opinion, and hurricanes as well. I think those are probably doable problems, but, and I've shown you this one earlier, but it does remind us, and I talked about it then, so I don't really have to talk about it so much this time. This is a measure here of uncertainty. So there's really a large uncertainty. So when someone was interviewing me the other day for Fox News, and I think it's going to be broadcast this weekend, so it may not be the person you recognize here, but I may be on the cutting room floor, I'm not sure. In any case, so I did emphasize the uncertainties there, but the question was, is it human, is it anthropogenic, or is it not? Is it yes or no, he asked me. And the answer is, it's yes, but the question shouldn't be yes or no. The question is, how much? That's really what the question is how much is the warming going to be? Well, that's really a good question, and you can see how much uncertainty that we are going to have to deal with here. And some people, and I don't want to go on and on about this, but there are some people who claim that if the temperature goes above about 2 degrees Celsius, above its pre-industrial value, that we are in a kind of danger zone where we may reach some so-called tipping points where Greenland might begin to irreversibly decay, even if we were to stop and go back. Or some other things like that might happen. I don't know about that, but I just put that out there for your consideration. Let's see. This is a climate model simulation, I think. I hope. Well, I'm not getting it to happen. Am I? No, it didn't happen. Sorry. Well, we'll go on. So what that one would show, which was going to show, was that the models that we're now going to be using in the next IPCC report, the one about 4 years from now, will actually be much more faithful, looking like weather is what I mean. Those storms that are coming past us now about every 3 or 4 days, those will be you'll see those in these simulations. So it really is starting to look like real weather in these models. And I'll give you another hint about that here. So what we think is that as our model, the models have to work by casting them onto a grid over the Earth. This is Europe here, this is Greenland over here. So you have to put it onto a grid. And this was the coarseness of our grid in 1990, when this was as well as we could do with the computers of that time. And then by the time you get to 95, things are a bit better. Then 2001, we were at this level. And now in the 2007 report, we were at about this level. So the resolution was about 100 kilometers, a little bit more. We're getting down to maybe a few counties in Texas now. So they are beginning to capture the real features of day-to-day weather. So we probably might hope to at least get the statistics of the weather right, but not the timing of events. So Texas will probably warm about as much as the global average. So when you hear about the global average in one of these global average curves, roughly speaking, Texas should be about at the global average. In other words, it will probably warm more toward the poles and less at the equator. This is something that's been known to climate modelers for more than 20 years, that there would be a kind of enhancement of warming at the polar regions and not so much in the tropics. Middle latitude storm tracks are likely to move a little bit polewards. These things that we enjoy coming across Texas, this is where I think that we will have some impact here. Middle latitude storm tracks, they come here in the wintertime. If you think about this, about the beginning of June or early week or two in June, we see our last front. And we don't see another one until the middle of September. And now we're in December, they're really cranking through here. Every week we're getting new things. So what if the band of storms coming from west to east across the United States, those lows and highs marching across, what if that band moves a few hundred kilometers further north? That's what models are saying might happen. What that would do then is it would lengthen our summers here, our kind of tropical climate in summer, where what we get is basically the afternoon thunderstorm. That's about what we get for rain here in the summertime. Same way in College Station, although we get a little more of it over there. And the Gulf does play a role, and that's a little bit hard to include well in these models. So here is that conclusion that I mentioned earlier, that West Texas is likely to be drier. A lot of air comes up from the Gulf, and if the tropical zone expands northward a little bit, we're likely to get more dry air in the west and to be sinking air, which you can't make rain when the air is sinking. Rain is caused by rising air cells, and so that's going to, but in the eastern part of the state, it could be different. So the southeast part of the United States, according to these models, would get a little bit more rain, a little bit more, but it would be warmer, so evaporation may very well wipe out what helps us. So in both cases, the incidence of long extremes, and I did mention that before, so I won't go on with it. Here is a graph from Jay. They've gathered together from these models and restricted it down to Texas, and what you see is here's the business as usual one. They don't look so very different from the global average, so this is what I would also expect. Here's the business as usual and the intermediate and the low. So we might expect that toward the end of the century, and I don't have one graphic with me, I just saw it the other day, but this past summer has been a really hot summer, as you well know. And John Nielsen Gammon, our state climatologist, put together a graphic, and he showed that out here toward the end of the century would be like some of the cities in Texas this past summer. Imagine if it was like that every summer. And that's another of Jay's graphics coming up. This is a drought index that you can also model with these general circulation models. And what you see is that drought in Texas might tend to be more so. This is an index that involves not just precipitation, but the soil, wetness. And so this suggests that as we go out further, average over the state, and probably you ought to do this for east and west, but unfortunately when you take smaller areas, the signal to noise is a big problem. So that's one reason these are often done. So here is a little graphic that shows us something about the number of 100-degree days. And I don't know, in Texas here we did have a few places that probably had quite a few days where it went over 100 degrees. And so what it was like here this summer may be indicative of what it might be like toward the end of the century. I'm not blaming this summer on global warming. Please don't get that impression. This was just an accidental fluctuation, I would say, this past summer. But this might be what the climate is toward the end of the century in this part of the country. All right, so are you ready? And here is this will give you a little idea of the global distribution of precipitation, especially in the tropics. This was collected from the satellite that Bob mentioned that I was involved with back in the late 80s and then into the 90s. It was finally launched in late 1997, and it's still flying here in almost 2010. Remarkable satellite. Here is a zone around the equator, and this feature is here all the time. It moves around a little bit with the seasons. In Africa, you know, it moves up and down with the seasons, and the animals migrate to follow it. You all know those stories. And out over the Pacific, it's a rather narrow band throughout the year of heavy rainfall called the Intertropical Convergence zone. And then it goes all the way around, girdling the Earth and giving us this tropical rainforest in here and here. It's very intense here, but it moves back and forth. And here the Amazon rainforest. But look here at the areas where the air rises here and then sinks, going up to about 30 degrees latitude. So here are the world's deserts, ocean and land. Right? So there they are. So this is a rather good schematic to ask, well, what happens if we change the climate? This is the present climate, of course. And this is a little schematic just now focusing in on just the United States. And if you look, this is in the wintertime. Notice here, this is I-35 right here. Okay, so to the east of I-35 it rains, and you may well be aware that to the west of I-35 it doesn't. Right? And in fact, this pretty closely parallels the line east of which precipitation exceeds evaporation, and on the west side of it, the reverse. And over here there are trees, and over here there are no trees. And so the winter storm tracks come across here, and in summertime, this band moves up. This is what I was talking about a few minutes ago. But what if this whole thing moves up a little bit? Well, it could increase our summertime. Notice a couple of other features. Here's the precipitation in the west, Seattle during the wintertime, always raining out there. And in the summertime, the ITCZ creeps up the Mexican, the Central American Mexican, and here is El Paso getting a drink of water. They get 6 inches a year out there, most of it in a couple days when that happens. So, all right, so models, I've already said this. And this is yet another picture from these same models. I won't go over and over this. Disregard that. This is winter. So what it says is, well, it may or may not rain more or less right in our region here. And then going on, this one tells us something about rain again. But basically, things in here in our will get less rain to the west. And going here is summertime. Here is rain in the summertime. So again, you see out in the western part of the sort of Mexican extension into North America, drier, and you see the same pattern here. So this seems to be a fairly robust feature. And you can see here is the ITCZ I talked about. So one rule of thumb, I think, that's not unreasonable is where it is already wet, it's going to get wetter. Where it's dry, going to get drier. So, so it recedes up this way. You see more rain up here, but less in the track behind it. So same thing. Okay, so now concerns. Well, we're winding down. I'm going to try to get finished. The introductions were so long. And so many people were thanked and deserved every second of it. Hotter and with longer summers. That's what I think we'll see here. So in other words, that qualitative difference between our tropical summer and the rest of the year might get a little longer. Drier winters, especially in the west. Sea level rises of a foot, but maybe, and just in the last couple of weeks, the new report, Greenland is melting more than was expected at the time of the 2007 report, and now those things that used to be in 2007 report about a foot sea level rise by the end of the century, now a little bit bigger. So you want to keep your eye on that. That will have an effect on Texas and our planning, right? When you're building harbors and you're thinking about hurricanes and what kind of damage they're going to do. A couple of feet make a big difference in the storm surge coming in. So just for planning purposes, hurricanes, more or less, more intense, we don't know yet. It's too soon. And there are a lot of people working on this, and I do think this is a solvable problem, along with the El Nino one. Now, I think that water in Texas is going to be very costly. I think the rivers will be drying up. There may be times when, and by the way, in the drought of the 50s in Texas, it's my understanding that some of the rivers that crossed did not make it. The Rio Grande already has dry spots some years, in fact, a lot of years. And there are hydrologists probably in here who know far more than I do about the past. But we might expect more dry riverbeds, at least for spaces in the summertime or at some times of the year. This is really important for Texas. Where are all of our power plants? They all have to be sitting on rivers. And you may remember a couple of years ago, Bob, you were in Atlanta at the time, right? They had a little drought over there. It was actually a pretty serious drought. But there were rivers that ran by nuclear reactors over there. They actually had to shut them down, didn't they? They actually did shut some nuclear reactors down because they have to have cooling water. They dump it back into the river. It's not all lost, but they put pretty warm water back into the river. But still, I don't know how much, what if that's a problem or not. But so let's get down to the last issue. Well, there's the old do-nothing strategy. You know, sit tight. You know, the grandkids, they'll just move away somewhere. They probably will anyway, right? And mine are out in Oregon. I don't know. Don't listen to these scientists. Instead, smear and vilify them. This was written several weeks ago, by the way. Several weeks ago. They just created a hoax. Well, I don't know. Whine. All this will cost too much, and it's going to mean higher taxes. Well, could be. Cash in on quick profits, right? Take your money now, and, you know, devil take the hindmost. Is that what was that? All right. 2100, they'll find their own way. Well, that's probably true. Probably true. So, well, another way is to take an intermediate position, that is agree, but you still don't do anything. You can delay the action, right? You can blame it on those other guys over there not doing it, so why should we do it? California is doing it, but also, well, that doesn't work, does it? Future technology will save everything. Now, these are guys who are really optimistic about our understanding of climate and climate models. These are folks who say, well, you can put something on the top of the clouds and make them more reflective and save us from global warming. Well, I guess I know just enough about climate models that I'm not so sure I'm ready to try any of that stuff. Or we might put dust into the stratosphere. Send up some airplanes, put some dust up there, and every now and then we have to do it again, and that'll screen out the sunlight. So it could get dimmer and dimmer down here. Of course, that wouldn't help us with the ocean, right, which is absorbing about half of the CO2 that we are emitting is going into the ocean and the rest of the biosphere, a lot of it into the ocean. And it is, just like in our Pepsi Cola, making it more acidic. And if this continues, there will be consequences of a more acidic ocean. I won't go into that one. Hope that we'll run out of fossil fuels before it's too late. Well, actually, there is a rather interesting theory floating around and we had a visit from this guy a few weeks ago at Texas A&M, a guy named David Rutledge, who was a former dean at Caltech, very smart guy, and he's been looking at coal reserves and oil reserves. We all know about peak oil, you hear about that, but he thinks there's peak coal. So he says, no problem, we're going to run out of this stuff before it gets too late. That's good. Could cost us a lot, though, to make the rather rapid adjustment that would be necessary. So the final thing is, well, you do the right thing. And what I would advocate is to be realistic about the science. Let's listen to people, but of course, you know, all of these, there are uncertainties in all of these things we do. Businesses deal with uncertainty all the time. That's their nature. That's what they do. So you take some prudent actions. There is some time. We don't have to do it overnight. We don't have to turn the world upside down and put everybody in the world out of work. We have a little bit of time. I think that, but as time goes on, if I'm right about this, and those 97% of my pals are right about this, then in 10 more years, we'll have more data, more understanding of the problem, and it may be that time, by that time, more and more of us will accept this and act on it. Or maybe we'll find out the whole thing's wrong and we'll be okay. But I think that, you know, there are a lot of things we can do. There are plenty of actions that we can take in our own country. And I don't want to get into politics here. But on the other hand, you know, there are many things that we can do in our country that would be very good for our national security and other things that are quite parallel with this. So why not do them? You know, windmills. There's enough windmills in windy areas in Texas that we'd never have to make another coal-fired power plant. I've done the calculation for my class. Hundreds of gigawatts of energy from wind alone. You can do more with solar than that. I don't know about the economics but I know this. If you look at the amount of energy you can generate from wind, you can make calculations and deal with this. And you can get on the web and find places where the calculations are done. You can generate about a couple of watts per square meter from windmills. And you have to space them properly and everything. But you can literally get hundreds of gigawatts of energy right here in Texas. So here's another lesson. You should be really careful about the sources of your information. For example, you see a lot of ads on television about clean coal. Well, clean coal is coal that's actually complying with the law. That the sulfur in the coal is down to a certain level, and ash and other ingredients are kept at and mercury in particular. But they're not talking about carbon dioxide when they talk about clean coal. That's not what's meant. Although it may be the impression you get when you see that ad. So be a little careful. Don't just rely on the past in long-term planning, for example, water resources and harbors. When in the Texas planning, the Water Development Board and most hydrologists traditionally use the drought of record in their planning. The 1950s was the drought of record in Texas. And so what I'm saying is that that may not be the most reliable indicator of what you might expect in the future. So that's just a word for the weary, I'm sure. So often doing the right thing has some other virtues, right? So saving energy, water it saves money. Remember, if you save money on something, maybe by conservation, that means that's money you made and didn't have to pay tax on. Think about that. A lot of people don't think about that very much. And you know, it's like driving a little bit slower. Well, you get a lot more miles per gallon from your car, and you didn't have to pay tax on it. The public transportation, that saves energy. We talked about national security. Texas can continue to be a world leader, and that's what I've already talked about, the wind, and so I do believe that. All right, so now I'm going to finish up. So there are some students in here and teachers, and I really do think, you know, considering it's really blossomed out to us a level of scientific illiteracy in our country and in the world in general. I mean, this really has shown up this week, in my opinion. And it's, I find it a little disturbing, more than a little, especially as a professor. So if you're a student, you might want to consider a career in this business. I'm toward the end of mine, and I can tell you I've enjoyed it tremendously. And it's very competitive. It is a contact sport. It's very exciting. It's very thrilling when you find something that nobody else in the world has ever known, and you do. That's a pretty exciting moment in your life. Doesn't happen too often, except to Bob. It happens to him all the time. There's no feeling quite like discovering something. We've all experienced it in our own way. Even, you know, walking into a canyon or something, you know, where you think maybe nobody's been here for a long time, and you're seeing it for the first time. It's an incredible feeling. And it really does beat working on Wall Street. There's a lot more money on Wall Street. I have one colleague who, after getting his degree at Rice, his bachelor's in physics, he went off to Wall Street and worked for 3 years. He was making a ton of money, but he didn't like his life, and he went to Harvard and got his PhD in chemistry, but really in climate work. Water vapor was his thing, upper atmosphere. And so now he's one of my colleagues, professor, and he's making about 1/10 of what he would have made in that business, but I really think he's a happier person for it. So anyway, all right, so we need you, and that's it. So I appreciate you. I went over a little bit. Sorry about that. Thank you, Jerry.
Thank you, Jerry. We'll be happy to answer questions.
Sure.
So,
don't get too hostile, but I don't mind a little bit. Yes. I'm having trouble hearing. Maybe I need, how about taking the microphone? Is that possible? I can't quite make out your words, sorry.
Okay, sure. I'll take your microphone.
Let's try it.
This is the room.
This is the room. I'm not sure which is which.
This is the room I'm in.
Okay. Oh, that's right. Sorry, now let's try it.
Okay, I noticed that on the medium model,
Yes.
in the first half of the century, maybe, it kind of looked like the medium model was a bit higher than business as usual.
I didn't notice, but you might
What do you
be.
think
I don't
was-
know the reason for that. That's one I don't know the answer to. I wish I did. Now, the youngest person in here just asked me the most difficult. I have the feeling that guy is going on the track that I was on many years ago. Yes, we need you. How about another? There was another back here. You think we can? Maybe I can hear you. You have a good, strong voice.
My understanding of sea rise is that it will be worse in certain areas than others because of the currents in the ocean.
Yes.
Is Texas gathering data to see what's happening with the amount of sea rise we already have, to see how that plays out? And is there any planning going on for Houston or other places?
Sea level around the Houston coast is pretty complicated because we actually have, as is the case in many parts of the world, the land is sinking. So actually the land is sinking much faster than the ocean is rising, especially around Houston and other places. Part of this could be from pumping water out from aquifers that are below. But there is a pretty big program at Corpus Christi, Texas A&M Corpus Christi. I think it's called the Hart Institute. So there is a pretty big program there. We've been looking at tidal gauges and things like that for a century or more. So that's kind of an art form that's developed. And they look every day, the tides coming in, they're so-called tide gauges. And you can average over time with these and get the noise down and actually get this down to well below a millimeter. And so that's happening all over the world. But it's really complicated by sinking land accompanying. And in other places, of course, land is rising. You know, where the ice sheet melted away off of the northern part of our continent, the Earth is still rebounding from all that weight. It's still rising. So in some places it's rising, others sinking. But you're also right that sea level depends on where you are in the ocean. The currents do have an influence, and the satellites flying over, some of which are originated right here at the University of Texas, as you may know, very important work being done right here, measuring sea level and the distribution of mass in Greenland. So the GRACE mission is headquartered right here at the University of Texas. Great mission. By the way, I had a competitor up against it and I lost, and they won. I came in number 2. Yes.
You said about the expansion of ocean water due to temperature.
Yes.
Now, your temperatures, most of the temperatures on your charts are atmospheric temperatures.
Yes.
So the ocean level temperature is going to be below that.
It will lag behind. Basically, it'll lag behind. That's right.
And
So energy is going into the ocean just as, so it gets stirred down by the mixed layer of the ocean into the deeper parts. So that's happening. And we actually have, for the last 50 years, we actually have pretty good measurements of the ocean temperatures going down hundreds of meters. So we have a pretty good feeling for how that heat is diffusing down. It's not in simple diffusion like on an ice or a bar of material, but it's mixed down by the eddies in the ocean. So we have a pretty good idea about that. By the way, I failed to mention, there are 2 ways to make the sea level rise. One is heating the ocean and making it expand a part or 2 per thousand, whatever it is. And the other, per degree, the other is the melting of glaciers. Of course, now the melting of sea ice does nothing, right? That's like the ice in your cocktail. When the ice melts, the water doesn't rise up, overflow. So nothing happens, floating ice. But the ice that's sliding off of Greenland, those glaciers into the sea, is causing sea level to rise. If all of Greenland melted, sea level would go up about 6 meters. And if all of the West Antarctic ice sheet, which is also somewhat vulnerable, there's about 6 meters of ice there. So altogether, 15 meters, something like that, between those two. And then there are the mountain glaciers, which can all, and they've been retreating like crazy, as you know. The larger mass of Antarctica is so far below freezing that even if you warm it a bit, it isn't going to melt. So there's a lot of ice that will stay there. Yes?
If you melt the northern polar cap and the dissemination of the melted water, would that tend to cool
It could do that, yes. In fact, we do think that's happened in the past. As the great ice sheet in North America melted, there were a lot of big events out the St. Lawrence Seaway and into Hudson Bay where these things happened. And you can see it might be that some of these large events like the so-called Younger Dryas and some of these, as the ice melted, all of a sudden Greenland cools off again. Our data suggests that. And then starts to warm up after 500 years or so. So these big events do things like that. We don't exactly understand why. I suspect that some of these are solvable problems as our ocean models get better. Yes?
The graph that you had that showed the climate changes from the 1900s to the present.
Yes.
There's a slight spike in the 40s.
Yes.
What caused that?
It seems to be in the northern polar region. And a lot of climatologists really think this is not real. This was at the time when, during World War II, there was a lot of action going on around, and there was disruption. Well, but it isn't just in the ocean. Apparently some of it is on the land too. So you can't just blame it on the ships and the procedures they use to measure the ocean temperature. So it's got a persistence to it in the business. So there are a lot of people who'd like to see that go away. It hasn't gone away though. So here we are. Yes.
What's your feeling about methane from the tundra?
Well, that's a kind of frightening proposition too. Also not really talked about in the IPCC. So methane and carbon dioxide are probably stored in permafrost and other areas in polar latitudes, particularly North America, Siberia, so on. So as the ice retreats, this stuff comes bubbling out. And of course, there's a lot of methane also in other places in clathrates in the ocean floor. Let's hold off on that one for a minute and just talk about the land. Well, this could be the explanation for why the carbon dioxide and methane go up as the big ice sheets retreated. And then, of course, if the ice sheet retreats a little bit, the methane and CO2 come bubbling out. It's a positive feedback. This makes the warming more intense. So this is probably the answer to the tracking of the temperatures. We didn't talk about that in this lecture, but I saw one of the young freshmen had a graph of the CO2 and the temperature going back hundreds of thousands of years. And that is probably just this very feedback that you're talking about. So probably the big moves of the ice sheet are triggered by the Earth's orbital element changes. So the tilt of the Earth's spin axis, the precession of the equinoxes. See, right now we're closest to the sun in wintertime, northern hemisphere winter. 11,000 years ago it was summer. You can see that in the record, temperature record. All right, I'm going way off the track. Sorry. Yeah, next.
Is there anything consumers can do today to reduce CO2? Things like zero waste or electric cars, eat less meat, goes on and on. What makes that big impact?
It's amazing to me. You remember in the 70s we started recycling, and I thought, oh, people won't do that. But they did, actually. It's amazing, isn't it, what people did do in recycling. But I have the feeling that volunteerism, as attractive as it seems, and we all should probably do it, nevertheless, I suspect that we have to put some kind of incentive beyond altruism to do the kind of changes that have to be done. In our country, we use about more than twice the amount of energy per capita as places like Europe. It's more than twice. So naturally, the amount of fossil fuel that we use, the amount of CO2 that we put in the air, is probably 2.5 times per person more of Europe. So we live a pretty easy life in that respect. But if you go over there, life isn't so bad over there. But I think it probably has to be. We don't like that. None of us like to be taxed for doing this or doing that. But maybe that is the answer. I don't want to be a politician in here, so I'd rather be the deliverer of the science. Yes, sir.
In the short chart, you showed clearly an upward trend in temperature. In the much longer chart, where you had multiple
Yes, yes,
The right part of the chart shows that same upward trend.
yes.
But the left part, the
Yes.
much older ones, seem to have a downward trend. Do you have a reason
Well,
why it would do that?
I don't think that we fully understand what, in the last 50 years, we have a pretty good idea of the different forcings, right? We know something about the sun. We've been measuring the solar irradiance really accurately for the last, say, 35 years. Other things, we have temperature from the ocean. See, one way to make it warm, natural variability, take a big glob of warm water and bring it up to the surface. That raises the global average temperature and nothing happened, right? I mean, nothing drove that, perhaps. But that's kind of a silly example. But so we don't really know why the Little Ice Age occurred, why that cool period when the Thames froze over every winter and they had parties out on the river, frozen river. It doesn't happen anymore. So that long period, well, that was a period when there were no sunspots. Really rather enticing, rather suggestive that maybe it had something to do with the sun. Don't know. Then there's this warm period around the time of the High Middle Ages, around the year 1100, 1200. It was a little warmer then. Probably not as warm as now, but we can't really completely rule that out. In our report, we thought that it was plausible that now, the last few decades, were warmer than any time in the last 1,000 years, but only plausible. But we could say with quite a bit more certainty about the last 400 years. We know it was cooler. Too many different things tell us that. But the High Middle Ages, there were people living in Greenland, colonies from Denmark, right? They all died out. We don't know exactly, or they all left or died out. We don't know exactly why. Might have been the Black Death. Don't know. Yes, maybe there's an anthropologist here who knows the answer. Yeah.
What do you think motivates the opposition to the models that you're presenting?
Well, I think I'll get to you next. I'm sorry, I've seen your hand. There are people who think the feedbacks are operating differently from the majority of people. So there are a handful of scientists with legitimate credentials who are opposed to this theory. And I can name them on a couple of hands. Most prominent is Richard Lenzin, but there are a couple of others. And first of all, they're rather conservative about this. They don't believe these models as much as the greater majority. But then, of course, they're invested in it, right? So it is natural. But I think the main theory is that the feedbacks are not as positive as we think, and some people might even think that they're negative. That the interaction between cloud and water vapor may actually be slightly negative. It doesn't mean there won't be any warming, but much, much less than these models say. I don't think you could concoct a model that says when you put in more CO2, the temperature will go down. I think that would be impossible. I think that would be an unstable model. The Earth would do something to stop that from happening. So there are legitimate concerns, but only by a few people. It doesn't have very many followers. And you know how science works. People get on board and you find a piece of data that disagrees with your paradigm. Well, at first, you put it up on the shelf and it kind of irritates you. You look at it every now and then. And more often than not, in a powerful paradigm like this, or like, say, quantum mechanics or relativity or whatever, more often than not, it turns out the measurement was wrong. And so then people get back to normal and they keep on going. And that's happened several times in the climate business, that there was an irritating data inconsistency or something, but it turned out the data was wrong, or the interpretation of it. So let me get to this gentleman up here.
Last question for
Yeah.
Dr. North.
Thank you.
Are the climate changes we're seeing in the northern hemisphere and the proposed, like I said, the storm tracks moving north?
Yes.
Are the same effects being seen equally in the southern hemisphere?
Yes, they are. In fact, it was easier to spot, easier to see in the southern hemisphere, in the models. Now, actually, the data show, and we don't understand this at all, the data show that the storm tracks are receding even faster than the models say. This is Fu's work at Washington. They're actually expanding a little faster. So it might not just be this. There could be some other thing going on in the system. But this is kind of troubling. Let's hope that's not really true. Maybe it's one of those things that we'll throw out after we've looked at it a little more. Because God knows we don't need this to be happening more than we these models. By the way, when you look at the amount of CO2 emissions for the last 10 years, 15 years, we're above the business as usual. We're spitting the stuff out faster than business as usual scenario. These scenarios were put together about a decade ago, and we're going at it faster than that. So.
I'm sure Dr. North would be happy to answer some more questions
Sure,
individually. We're going to take a break now.